Hello everyone, welcome to my channel. Today we start another topic talking about special relativity, Episode 2, from Albert Einstein documents. Are you ready? Let's start together. So what effect did the Michelson-Morley results, which showed no evidence of the ether and no difference in the observed speed of light, no matter in what direction the observer was moving, have on Einstein as he was incubating his ideas on relativity? To hear him tell it, almost none at all. In fact, at times he would even recollect, incorrectly, that he had not even known of the experiment before 1905. Einstein's inconsistent statements over the next 50 years about the influence of Michelson-Morley are useful in that they remind us of the caution needed when writing history based on dimming recollections. Einstein's trail of contradictory statements begins with an address he gave in Kyoto, Japan, in 1922, when he noted that Michelson's failure to detect an ether was the first path that led me to what we call the principle of special relativity. In a toast at a 1931 dinner in Pasadena honoring Michelson, Einstein was gracious to the eminent experimenter, yet subtly circumspect. "You uncovered an insidious defect in the ether theory of light, as it then existed, and stimulated the ideas of Lorentz and Fitzgerald, out of which the special theory of relativity developed." Einstein described his thought process in a series of talks with the Gestalt psychology pioneer Max Wertheimer, who later called the Michelson-Morley results crucial to Einstein's thinking. But as author I. Miller has shown, this assertion was probably motivated by Wertheimer's goal of using Einstein's tale as a way to illustrate the tenets of Gestalt psychology. Einstein further confused the issue in the last few years of his life by giving a series of statements on the subject to a physicist named Robert Shankland. At first he said he had read of Michelson-Morley only after 1905, then he said he had read about it in Lorentz's book before 1905, and finally he added, "I guess I just took it for granted that it was true." That final point is the most significant one because Einstein made it often. He simply took for granted, by the time he started working seriously on relativity, that there was no need to review all the ether drift experiments because, based on his starting assumptions, all attempts to detect the ether were doomed to failure. For him, the significance of these experimental results was to reinforce what he already believed, that Galileo's relativity principle applied to light waves. This may account for the scant attention he gave to the experiments in his 1905 paper. He never mentioned the Michelson-Morley experiment by name, even where it would have been relevant, nor the Fizeau experiment using moving water. Instead, right after discussing the relativity of the magnet and coil movements, he merely flicked in a phrase about the unsuccessful attempts to detect a motion of the Earth relative to the light medium. Some scientific theories depend primarily on induction, analyzing a lot of experimental findings and then finding theories that explain the empirical patterns. Others depend more on deduction, starting with elegant principles and postulates that are embraced as holy and then deducing the consequences from them. All scientists blend both approaches to differing degrees. Einstein had a good feel for experimental findings, and he used this knowledge to find certain fixed points upon which he could construct a theory. But his emphasis was primarily on the deductive approach. Remember how in his Brownian motion paper he so oddly, yet accurately, downplayed the role that experimental findings played in what was essentially a theoretical deduction? There was a similar situation with his relativity theory. What he implied about Brownian motion, he said explicitly about relativity and Michelson-Morley. "I was pretty much convinced of the validity of the principle before I knew of this experiment and its results." Indeed, all three of his epical papers in 1905 begin by asserting his intention to pursue a deductive approach. He opens each one by pointing out some oddity caused by jostling theories, rather than some unexplained set of experimental data. He then postulates grand principles while minimizing the role played by data, be it on Brownian motion or blackbody radiation or the speed of light. In a 1919 essay called Induction and Deduction in Physics, he described his preference for the latter approach. The simplest picture one can form about the creation of an empirical science is along the lines of an inductive method. Individual facts are selected and grouped together so that the laws that connect them become apparent. However, the big advances in scientific knowledge originated in this way only to a small degree. The truly great advances in our understanding of nature originated in a way almost diametrically opposed to induction. The intuitive grasp of the essentials of a large complex of facts leads the scientist to the postulation of a hypothetical basic law or laws. From these laws, he derives his conclusions. His appreciation for this approach would grow. The deeper we penetrate and the more extensive our theories become, he would declare near the end of his life, the less empirical knowledge is needed to determine those theories. By the beginning of 1905, Einstein had begun to emphasize deduction rather than induction in his attempt to explain electrodynamics. By and by, I despaired of the possibility of discovering the true laws by means of constructive efforts based on experimentally known facts. He later said, "The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results." The two postulates. Now that Einstein had decided to pursue his theory from the top down, by deriving it from grand postulates, he had a choice to make. What postulates, what basic assumptions of general principle would he start with? His first postulate was the principle of relativity, which asserted that all of the fundamental laws of physics, even Maxwell's equations governing electromagnetic waves, are the same for all observers moving at constant velocity relative to each other. Put more precisely, they are the same for all inertial reference systems, the same for someone at rest relative to the Earth as for someone traveling at a uniform velocity on a train or spaceship. He had nurtured his faith in this postulate, beginning with his thought experiment about riding alongside a light beam. From the very beginning it appeared to me intuitively clear that, judged from the standpoint of such an observer, everything would have to happen according to the same laws as for an observer who, relative to the Earth, was at rest. For a companion postulate, involving the velocity of light, Einstein had at least two options. 1. He could go with an emission theory, in which light would shoot from its source like particles from a gun. There would be no need for an ether. The light particles could zoom through emptiness. Their speed would be relative to the source. If this source was racing toward you, its emissions would come at you faster than if it was racing away. Imagine a pitcher who can throw a ball at 100 miles per hour. If he throws it at you from a car racing toward you, it will come at you faster than if he throws it from a car racing away. In other words, starlight would be emitted from a star at 186,000 miles per second. But if that star was heading toward Earth at 10,000 miles per second, the speed of its light would be 196,000 miles per second relative to an observer on Earth. An alternative was to postulate that the speed of light was a constant 186,000 miles per second irrespective of the motion of the source that emitted it, which was more consistent with a wave theory. By analogy with sound waves, a fire truck siren does not throw its sound at you faster when it's rushing toward you than it does when it's standing still. In either case, the sound travels through the air at 770 miles per hour. For a while, Einstein explored the emission theory route. This approach was particularly appealing if you conceived of light as behaving like a stream of quanta. And as noted in the previous chapter, that concept of light quanta was precisely what Einstein had propounded in March 1905, just when he was wrestling with his relativity theory. But there were problems with this approach. It seemed to entail abandoning Maxwell's equations and the wave theory. If the velocity of a light wave depended on the velocity of the source that emitted it, then the light wave must somehow encode within it this information. But experiments and Maxwell's equations indicated that was not the case. Einstein tried to find ways to modify Maxwell's equations so that they would fit an emission theory, but the quest became frustrating. This theory requires that everywhere and in each fixed direction light waves of a different velocity of propagation should be possible, he later recalled. It may be impossible to set up a reasonable electromagnetic theory that accomplishes such a feat. In addition, scientists had not been able to find any evidence that the velocity of light depended on that of its source. Light coming from any star seemed to arrive at the same speed. The more Einstein thought about an emission theory, the more problems he encountered. As he explained to his friend Paul Ehrenfest, it was hard to figure out what would happen when light from a moving source was refracted or reflected by a screen at rest. Also, in an emission theory, light from an accelerating source might back up on itself. So Einstein rejected the emission theory in favor of postulating that the speed of a light beam was constant no matter how fast its source was moving. I came to the conviction that all light should be defined by frequency and intensity alone, completely independently of whether it comes from a moving or from a stationary light source, he told Ehrenfest. Now Einstein had two postulates, the principle of relativity and this new one, which he called the light postulate. He defined it carefully. Light always propagates in empty space with a definite velocity v that is independent of the state of motion of the emitting body. For example, when you measure the velocity of light coming from the headlight of a train, it will always be a constant 186,000 miles per second, even if the train is rushing toward you or backing away from you. Unfortunately, this light postulate seemed to be incompatible with the principle of relativity. Why? Einstein later used the following thought experiment to explain his apparent dilemma. Imagine that a ray of light is sent along the embankment of a railway track, he said. A man standing on the embankment would measure its speed as 186,000 miles per second as it zipped past him. But now imagine a woman who is riding in a very fast train carriage that is racing away from the light source at 2,000 miles per second. We would assume that she would observe the beam to be zipping past her at only 184,000 miles per second. The velocity of propagation of a ray of light relative to the carriage thus comes out smaller. Einstein wrote, "But this result comes into conflict with the principle of relativity," he added. For, like every other general law of nature, the law of the transmission of light must, according to the principle of relativity, be the same when the railway carriage is the reference body as it is when the embankment is the reference body. In other words, Maxwell's equations, which determine the speed at which light propagates, should operate the same way in the moving carriage as on the embankment. There should be no experiment you can do, including measuring the speed of light, to distinguish which inertial frame of reference is at rest and which is moving at a constant velocity. This was an odd result. A woman racing along the tracks toward or away from the source of a light beam should see that beam zip by her with the exact same speed as an observer standing on the embankment would see that same beam zip by him. The woman's speed relative to the train would vary, depending on whether she was running toward it or away from it. But her speed relative to the light beam coming from the train's headlight would be invariant. All of this made the two postulates, Einstein thought, seemingly incompatible. As he later explained in a lecture on how he came to his theory, the constancy of the velocity of light is not consistent with the law of the addition of velocities. The result was that I had to spend almost 1 year in fruitless thoughts. By combining the light postulate with the principle of relativity, it meant that an observer would measure the speed of light as the same whether the source was moving toward or away from him, or whether he was moving toward or away from the source, or both, or neither. The speed of light would be the same whatever the motion of the observer and the source. That is where matters stood in early May 1905. Einstein had embraced the relativity principle and elevated it to a postulate. Then, with a bit more trepidation, he had adopted as a postulate that the velocity of light was independent of the motion of its source. And he puzzled over the apparent dilemma that an observer racing up a track toward a light would see the beam coming at him with the same velocity as when he was racing away from the light, and with the same velocity as someone standing still on the embankment would observe the same beam. In view of this dilemma, there appears to be nothing else to do than to abandon either the principle of relativity or the simple law of the propagation of light. Einstein wrote, "Then something delightful happened." Albert Einstein, while talking with a friend, took one of the most elegant imaginative leaps in the history of physics. The step. It was a beautiful day in Bern, Einstein later remembered, when he went to visit his best friend Michel Besso, the brilliant but unfocused engineer he had met while studying in Zurich and then recruited to join him at the Swiss patent office. Many days they would walk to work together, and on this occasion Einstein told Besso about the dilemma that was dogging him. "I'm going to give it up," Einstein said at one point. But as they discussed it, Einstein recalled, "I suddenly understood the key to the problem." The next day, when he saw Besso, Einstein was in a state of great excitement. He skipped any greeting and immediately declared, "Thank you. I've completely solved the problem." Only 5 weeks elapsed between that eureka moment and the day that Einstein sent off his most famous paper on the electrodynamics of moving bodies. It contained no citations of other literature, no mention of anyone else's work, and no acknowledgments except for the charming one in the last sentence. "Let me note that my friend and colleague M. Besso steadfastly stood by me in my work on the problem discussed here, and that I am indebted to him for several valuable suggestions." So what was the insight that struck him while talking to Besso? "An analysis of the concept of time was my solution," Einstein said. "Time cannot be absolutely defined, and there is an inseparable relation between time and signal velocity." More specifically, the key insight was that two events that appear to be simultaneous to one observer will not appear to be simultaneous to another observer who is moving rapidly. And there is no way to declare that one of the observers is really correct. In other words, there is no way to declare that the two events are truly simultaneous. Einstein later explained this concept using a thought experiment involving moving trains. Suppose lightning bolts strike the train tracks embankment at two distant places, A and B. If we declare that they struck simultaneously, what does that mean? Einstein realized that we need an operational definition, one we can actually apply, and that would require taking into account the speed of light. His answer was that we would define the two strikes as simultaneous if we were standing exactly halfway between them and the light from each reached us at the exact same time. But now let us imagine how the event looks to a train passenger who is moving rapidly along the track. In a 1916 book written to explain this to non-scientists, he used the following drawing, in which the long train is the line on the top. Suppose that at the exact instant, from the viewpoint of the person on the embankment, when lightning strikes at points A and B, there is a passenger at the midpoint of the train, MT, just passing the observer who is at the midpoint alongside the tracks. If the train was motionless relative to the embankment, the passenger inside would see the lightning flashes simultaneously, just as the observer on the embankment would. But if the train is moving to the right relative to the embankment, the observer inside will be rushing closer toward place B while the light signals are traveling. Thus he will be positioned slightly to the right by the time the light arrives. As a result, he will see the light from the strike at place B before he will see the light from the strike at place A. So he will assert that lightning hit at B before it did so at A, and the strikes were not simultaneous. We thus arrive at the important result. Events that are simultaneous with reference to the embankment are not simultaneous with respect to the train, said Einstein. The principle of relativity says that there is no way to decree that the embankment is at rest and the train in motion. We can say only that they are in motion relative to each other. So there is no real or right answer. There is no way to say that any two events are absolutely or really simultaneous. This is a simple insight, but also a radical one. It means that there is no absolute time. Instead, all moving reference frames have their own relative time. Although Einstein refrained from saying that this leap was as truly revolutionary as the one he made about light quanta, it did in fact transform science. This was a change in the very foundation of physics, an unexpected and very radical change that required all the courage of a young and revolutionary genius, noted Werner Heisenberg, who later contributed to a similar feat with his principle of quantum uncertainty. In his 1905 paper, Einstein used a vivid image, which we can imagine him conceiving as he watched the trains moving into the Bern station past the rows of clocks that were synchronized with the one atop the town's famed tower. Our judgments in which time plays a part are always judgments of simultaneous events, he wrote. If, for instance, I say, that train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events. Once again, however, observers who are moving rapidly relative to one another will have a different view on whether two distant events are simultaneous. The concept of absolute time, meaning a time that exists in reality, and tick-tocks along independent of any observations of it, had been a mainstay of physics ever since Newton had made it a premise of his Principia 216 years earlier. The same was true for absolute space and distance. Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. He famously wrote in Book 1 of the Principia, absolute space, in its own nature, without relation to anything external, remains always similar and immovable. But even Newton seemed discomforted by the fact that these concepts could not be directly observed. Absolute time is not an object of perception, he admitted. He resorted to relying on the presence of God to get him out of the dilemma. The deity endures forever and is everywhere present, and by existing always and everywhere, he constitutes duration and space. Ernst Mach, whose books had influenced Einstein and his fellow members of the Olympia Academy, lambasted Newton's notion of absolute time as a useless metaphysical concept that cannot be produced in experience. Newton, he charged, acted contrary to his expressed intention only to investigate actual facts. Henri Poincaré also pointed out the weakness of Newton's concept of absolute time in his book Science and Hypothesis, another favorite of the Olympia Academy. Not only do we have no direct intuition of the equality of two times, we do not even have one of the simultaneity of two events occurring in different places, he wrote. Both Mach and Poincaré were, it thus seems, useful in providing a foundation for Einstein's great breakthrough. But he owed even more, he later said, to the skepticism he learned from the Scottish philosopher David Hume regarding mental constructs that were divorced from purely factual observations. Given the number of times in his papers that he uses thought experiments involving moving trains and distant clocks, it is also logical to surmise that he was helped in visualizing and articulating his thoughts by the trains that moved past Bern's clock tower and the rows of synchronized clocks on the station platform. Indeed, there is a tale that involves him discussing his new theory with friends by pointing to, or at least referring to, the synchronized clocks of Bern and the unsynchronized steeple clock visible in the neighboring village of Muni. Peter Galison provides a thought-provoking study of the technological ethos in his book Einstein's Clocks, Poincaré's Maps. Clock coordination was in the air at the time. Bern had inaugurated an urban time network of electrically synchronized clocks in 1890, and a decade later, by the time Einstein had arrived, finding ways to make them more accurate and coordinate them with clocks in other cities became a Swiss passion. In addition, Einstein's chief duty at the patent office, in partnership with Bessot, was evaluating electromechanical devices. This included a flood of applications for ways to synchronize clocks by using electric signals. From 1901 to 1904, Galison notes, there were 28 such patents issued in Bern. One of them, for example, was called Installation with Central Clock for indicating the time simultaneously in several places separated from one another. A similar application arrived on April 25th, just 3 weeks before Einstein had his breakthrough. Conversation with Bessot. It involved a clock with an electromagnetically controlled pendulum that could be coordinated with another such clock through an electric signal. What these applications had in common was that they used signals that traveled at the speed of light. We should be careful not to overemphasize the role played by the technological backdrop of the patent office. Although clocks are part of Einstein's description of his theory, his point is about the difficulties that observers in relative motion have in using light signals to synchronize them, something that was not an issue for the patent applicants. Nevertheless, it is interesting to note that almost the entire first two sections of his relativity paper deal directly and in vivid practical detail, in a manner so different from the writings of, say, Lorentz and Maxwell, with the two real-world technological phenomena he knew best. He writes about the generation of electric currents of the same magnitude due to the equality of relative motion of coils and magnets, and the use of a light signal to make sure that two clocks are synchronous. As Einstein himself stated, his time in the patent office stimulated me to see the physical ramifications of theoretical concepts. And Alexander Moskowski, who compiled a book in 1921 based on conversations with Einstein, noted that Einstein believed there was a definite connection between the knowledge acquired at the patent office and the theoretical results on the electrodynamics of moving bodies. Now let's look at how Einstein articulated all of this in the famous paper that the Annalender Physik received on June 30, 1905. For all its momentous import, it may be one of the most spunky and enjoyable papers in all of science. Most of its insights are conveyed in words and vivid thought experiments, rather than in complex equations. There is some math involved, but it is mainly what a good high school senior could comprehend. The whole paper is a testament to the power of simple language to convey deep and powerfully disturbing ideas, says the science writer Dennis Overby. The paper starts with the asymmetry that a magnet and wire loop induce an electric current based only on their relative motion to one another. But since the days of Faraday, there had been two different theoretical explanations for the current produced depending on whether it was the magnet or the loop that was in motion. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, Einstein writes, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. The distinction between the two cases was based on the belief, which most scientists still held, that there was such a thing as a state of rest with respect to the ether. But the magnet and coil example, along with every observation made on light, suggest that the phenomena of electrodynamics, as well as of mechanics, possess no properties corresponding to the idea of absolute rest. Thanks you guys for take your time watching this video. Have a great day.